What if we could take everyday waste, things like wood chips or leftover corn stalks, and turn it into a powerful tool that not only fights climate change, but also supercharges our farms? It kind of sounds like something out of a sci-fi movie, but it's really happening. Today, we are going to dive deep into the engineering blueprint that makes it all possible and explore the incredible science of biochar.
So take a look at this. Now, it might just look like some big piece of industrial machinery, but this is a pyrolysis plant, and it's right at the heart of a truly revolutionary process. This is where we take something we have a ton of, waste biomass, and we transform it into something our planet desperately needs, a real scalable climate solution.
And the main thing that comes out of this process is something called biochar. Honestly, the best way to think of it is as a kind of super charcoal, one that's engineered for an incredible mission. It's so stable that it can lock away carbon in the soil for hundreds, even thousands of years. And on top of that, it acts like a sponge for water and nutrients, which can dramatically improve the health of our soil.
The idea itself is brilliant, right? No question. But turning that brilliant idea into a safe, reliable, working reality, well, that's a serious engineering challenge. And that really brings us to the big question for this whole explainer. How do you actually build one of these plants the right way so it's safe, efficient, and makes a product that's genuinely high quality?
Okay, so to understand the blueprint, we've got to start with the core science. It's a process with a pretty cool name, pyrolysis.
Now, that might sound complicated, but the basic idea is actually surprisingly simple. Just imagine heating something organic, like wood, in an oven where you've sucked out all the oxygen. Instead of bursting into flames and releasing all its carbon as CO2, it's just kind of breaks down. The heat transforms its chemical structure into something totally new and incredibly stable. And that, in a nutshell, is pyrolysis.
And here's where it gets really, really clever. See, pyrolysis isn't just about making one thing. It's this incredibly efficient process that takes one input, that waste biomass, and creates three valuable outputs. You get the solid biochar, for sure, but you also get a combustible gas called syngas and a liquid bio-oil. And get this, those other two products can be used to power the plant itself. It's a system that helps run itself. Okay, so we've got the science down. Now let's get into the engineering. How do you take that scientific principle and build a whole biochar plant around it? Well, as you're about to see, it's way more than just a machine. It's a completely integrated system.
You don't build something this complex on a whim. It takes a really rigorous, step-by-step engineering design process, which you can see laid out right here. It all starts with a master plan, called a functional specification. From there, you map out every single process. You do intensive safety studies, and only then do you get to the detailed design and the costing. Every single one of these steps is absolutely crucial.
And that very first step, the functional specification, is literally the bedrock of the whole project. The source material puts it perfectly. It's the coherent document that lets everyone appreciate how the entire process works. It sets the goals, it defines what a good final product looks like, and it lays down all the standards. It's the architect's vision, long before anyone even thinks about cutting a piece of steel.
Check this out. This is the next step in action. It's called a process flow diagram. And yeah, it might look a little intimidating at first, but its job is pretty simple. It maps every single flow of material and energy through the whole system. If you follow the lines, you can trace the journey. From the second the biomass is collected, to chipping, drying, pyrolysis, all the way to putting it on the soil. It's the plant's entire life story on one chart. And this one really drives the point home. On the left, you've got this simple concept. Wood chips go in. Easy enough, right? But on the right, whoa, that is the engineering reality. It's a process and instrumentation diagram, or P&ID. Every single line, every valve, every sensor you see there has been meticulously planned out. That's the level of detail it takes to make the simple idea on the left a safe and efficient reality.
So, you have these incredibly detailed plans. Now, how do you guarantee that when you go from paper to a physical working plant, it's not just going to be successful, but it's going to be fundamentally safe for the people who run it and for the environment?
Well, the answer comes down to one of the single most critical steps in the entire engineering process, the HAZOP study. That stands for Hazard and Operability, and believe me, it's a total game changer for safety.
The best way to think about a HAZOP study is like an insanely detailed pre-flight checklist for a jumbo jet. A whole team of engineers goes through every single piece of that complex diagram we just saw, and they ask, what if? What if this pressure valve fails? What if that temperature sensor is wrong? It's a systematic, almost obsessive way to find every potential problem before it can ever actually happen.
And the risks they're looking for are very real. I mean, we're dealing with high temperatures and combustible gases here, so the top concerns are always things like fire and explosion, controlling any kind of emissions, preventing dangerous gas leaks like carbon monoxide, and even managing noise. The entire design, the whole HAZOP study, it's all geared towards knocking out these risks.
All right, so with a safe, robust design locked in, we can finally get to the fun part: firing up that pyrolysis kiln and watching that incredible transformation happen. As the biomass kind of snakes its way through the kiln, it goes on a very specific journey of heat. First, up to about 150 degrees Celsius, it's really just drying out. Then, in a phase called torrefaction, it starts to really break down chemically. And finally, as the temperature climbs past 250 degrees, real pyrolysis kicks in, and that material is fundamentally and permanently transformed. But where does all the energy that was stored in that biomass actually go? This thing, a Sankey diagram, is a fantastic way to see that flow. Over on the far left, you've got 100% of the energy from the corn stalks. As you move across, you can see how that energy gets split up into different streams. Some is used for heat, some becomes syngas, and a massive chunk gets locked away in the final biochar.
And here's the number that really matters. Look at that big green arrow pointing to biochar. Of the 16,000 megajoules of energy in the original corn stalks, almost 9,000 of them, that's way more than half, are captured and stored in the solid, stable form of biochar. That right there is the carbon sequestering powerhouse of this whole process.
But look, making biochar is only half the battle. How do we actually know if the final product is any good? That it's helpful and not harmful? The proof, as they say, is in the pudding, or in this case, the product itself. This table here lays out the stakes perfectly. If you do it right with sustainable wood and you apply it correctly, biochar is a massive win-win. But if you do it wrong, it can have some seriously negative impacts. And that is exactly why having rigorous standards and quality control isn't just important, it's absolutely essential. And that really leads to the key takeaway here. High-quality, beneficial biochar isn't a matter of opinion. It's not a guess. It is a scientifically verified product, and it's backed up by hard data.
Just look at the level of detail on this slide. This is a real-world lab test for a biochar sample. They're not just checking one or two things, they're analyzing dozens of different parameters. They're looking at the pH, the total carbon content, key nutrients like potassium, and just as important, they're screening for any potential bad stuff, like heavy metals, to make sure it's safe. This is the level of scientific rigor we're talking about.
So what we've really seen today is a complete blueprint for transformation. It shows how, with disciplined engineering and rigorous science, we can take a common waste material and turn it into a stable, long-term solution for both our climate and our soils. It proves that what we so often see as waste is really just a resource in disguise. And it leaves us with a really exciting question. If we can do this, what other incredible blueprints for a better future are just out there, waiting to be drawn?